let's talk about power and energy. Power is a time rate of expending or absorbing energy. The symbol for power is P. Power is a product of the voltage across an element and the current through that element at any instance of time. We know that voltage is equal to the change in energy per unit charge, and we know that current is a change in charge per unit time. And by replacing both voltage and current with their respective formulas, we can cancel out dq, and we can derive the formula for power as dw over dt, the change in energy per unit time, where energy is measured in joules and time is measured in seconds. Power is measured in watts, and the symbol for watts is W. So let's take a simple element, a resistor with a positive and negative terminal, and here the sign of power is determined by the direction of current and the polarity of voltage, and here we introduce the passive sign convention, which follows that if the current enters the positive terminal of an element, then power is a positive value. If current enters the negative terminal of an element, then power at that element is a negative value. If power is a positive value at an element, then that element is absorbing power. If power is a negative value at an element, then that element is supplying or releasing power. The law of conservation of energy states that the sum of power in any given circuit at any instant of time must be zero. Therefore, the amount of power absorbed must be equal to the amount of power supplied at any given time. Going back to the formula for power, we can derive that the formula for energy would be the integral of power between some initial time to some final time. We can also replace power with voltage times current in this same formula. Another formula is that energy equals power multiplied to time. When it comes to paying electric bills, you may be familiar with the term watt hour or kilowatt hour, which is how commercial power is typically measured. Well, through this unit of watt hour, we know that watts are the units used to measure power, and hours are obviously used to measure time. And so we can see that watt hours are just a measurement of energy. If we transform hours to seconds in order to get both of these units into their basic SI unit form, then we can derive that 1 watt hour is equal to 1 watt times 3,600 seconds. And since energy is also measured in joules, then 1 watt hour is equivalent to 3,600 joules. Therefore, 1 watt second is equal to 1 joule. So now let's look at some examples that involve power and energy and how they relate to voltage and current in a circuit. This example states that the charge entering the positive terminal of an element is 5 sine 4 pi t millicoulombs, while the voltage across the element is 3 cos 4 pi t volts. Question is, how much power is delivered to the element at 0.3 seconds, and how much energy is delivered to the element between 0 and 0.6 seconds. Let's gather our given information here, which is charge Q of t. The equation for this is 5 sine 4 pi t, and the unit for this is millicoulombs. And for the voltage across that element, we have 3 cos 4 pi t volts. Now it's asking for power delivered to that element when time is equal to 0.3 seconds. Well, we know that the formula for power is voltage times current. We know that current is equal to the derivative of charge with respect to time. And so plugging in our value for charge here, let's find the derivative of 5 sine 4 pi t. So 5 is a constant. We'll bring it out front. And the derivative for sine is cosine. And chain rule here, we have to include the derivative of what's inside of sine, which is 4 pi of t. And so therefore we have I of t as being 20 pi cosine 4 pi t. And in terms of units, because charge is given by millicoulombs, then here we'll also have milliamps for this. Now that we've found the value for I, we can find the value for power now. So we're just going to rewrite this as V of t times I of t. V of t is given as 3 cosine 4 pi t times 20 pi cosine 4 pi t. Therefore, power, P of t, is equal to 60 pi cosine squared 4 pi t. And again, because even though we have V here as volts, we have I as milliamps. And so our unit for power is going to be milliwatts. So this now is our equation for power. And since we want to find the power when time is equal to 0.3 seconds, all we do is just plug in 0.3 right here. So P of 0.3 is equal to 60 pi is equal to 60 pi cosine squared of 4 pi times 0.3. And so we get the value of 123.372 milliwatts. That's how much power is being delivered to the element at 0.3 seconds. Now for our second question, how much energy is delivered to the element between 0 and 0.6 seconds, we need to first find the function for energy. And then we need to find how much energy is delivered between 0 and 0.6 seconds. Now, based on our formula for power, we have that energy is equivalent to the integral of power from some initial time to some final time. And so we have the equation for power right here. And we have our initial time as 0, and we have our final time as 0.6 seconds. So this is going to be pretty straightforward. From 0 to 0.6 seconds, we integrate 60 pi cos squared 4 pi t dt. And so we'll bring out 60 pi, that's a constant. And so here what we're going to do is we're going to use a trig identity. We know that cosine squared theta is equal to 1 plus cosine 2 theta over 2. In this case, theta is going to be our 4 pi t here. And so cosine squared of 4 pi theta is equal to 1 plus cosine of 2 times 4 pi t over 2, which is equal to 1 plus cosine 8 pi t over 2. And this whole thing will replace this whole thing. And so now we'll go back to our solution for energy, which would be 60 pi 0.6 1/2. I'm just going to rewrite this a little bit easier. Cosine 8 pi of t dt, once we've replaced that. Again, we'll bring out all the constants out front. 60 pi over 2 of 1 plus cosine 8 pi t dt. And we can separate this into 2 parts. That would be 60 pi over 2 and we'll make 2 integrals here. Cosine 8 pi t dt, our big bracket. And so let's go ahead and solve for this section first. That would be equal to t integrated from 0 to 0.6, which gives us a value of 0.6. And now if we solve for this section, eight pi t dt. Okay, well, what we're going to do here is we're going to use u substitution, and our u is going to be 8 pi of t. Therefore, du is equal to 8 pi dt. du over 8 pi is equal to dt. So now we can replace 8 pi t with u, and we can replace dt with du over 8 pi. And because we've done that, we're also going to change the initial and final values according to these new u variables. And so u initial would be 8 pi replacing t here with 0, since that's the initial value. That would be 0, which is equal to 0. And then u final would be equal to 8 pi, times 0.6, since that's t final. Then u final would be equal to 4.8 pi. Okay, so now let's go back to this. We have our new initial and final values, 0 and 4.8 pi. Cos u, replace dt with du over 8 pi. we'll bring out the constants, 1 over 8 pi. Okay, and once we integrate that, we would have sine of u integrated from 0 to 4.8 pi. And so we have 1 over 8 pi. And in the bracket, we have sine of 4.8 pi minus sine of 0. And we get a value of 0.0234 for this. So now going back to our solution, 60 pi over 2 and 0.6 plus 0.0234 in the brackets. And therefore, our value for energy, the amount of energy being delivered to that element between 0 and 0.6 seconds is 58.754 millijoules. And that's our final answer. For this example, we have two graphs of the current going through an element and the voltage across it. It asks to draw the graph for the power delivered to the element for when t is greater than 0. So let's start with that. So we're going to find power for when t is greater than 0. Well, we know that power is equal to voltage times current. And so we see here that at 0 seconds, the current going through that element is 0. And at 0 seconds, the voltage across that element is 5 volts. And so for when P is equal to 0, that voltage is 5 and that current is 0. Therefore, power is 0 milliwatts when time is at 0 seconds. We're going to use milliwatts here because even though our voltage is at the standard volts form, we have milliamps here for current. So now we'll find all the other values for power at all the other intervals. And so let's see here. When power is at 2 seconds, we have that current is 60 milliamps. And for voltage, we have two values. At 2 seconds, we have a voltage of 5 volts, and we also have a voltage of minus 5 volts. So we'll say that at 2 seconds, we have volts equal to 5 and amps equal to 6 and current equal to 60 amps. Therefore, we have 300 milliwatts for this. And for, again, when power is 2, again, because we have two values for that, we have that the voltage is negative 5 and the current stays at 60 amps. And so we have a value of negative 300 milliwatts for that. And lastly, at 4 seconds, we see here that power is 0, and we see that voltage is still at negative 5. And so we have power at 4 seconds is equal to negative 5 volts times 0 amps, milliamps, which gives us 0 milliwatts. And so these are the values that we have for the different times greater than 0. And so what we'll do is just draw the actual graph for it now. So at P equals 0, we have 0 milliwatts. P equals 2, we have 300 milliwatts and negative 300 milliwatts. And then for 4 seconds, we have 0 milliwatts. Let's all transfer that over. So 0 seconds here at 0 milliwatts, 2 seconds here at 300 milliwatts, but also negative 300 milliwatts. And then for 4 seconds, we're back down to 0 milliwatts. And so we can connect these dots here to have our graph. And that's it. That's our answer for this question. For the second question, it asks, what is the total energy absorbed by the element for the time period of 0 to 4 seconds? So we need to find how much energy. Well, we have our formula for energy as the integral of power from some initial time to some final time. Okay, so we're going to break it down into the two sections. We'll have from 0 to 2, some equation for power, plus from 2 to 4, our equation for power here. And now let's find our equations for power between 0 and 2, and between 2 and 4. So referring to this classic equation, let's find here between 0 and 2, let's find our equation for this line here. We have a rise. For our slope, we have a rise of 300 and a run of 2 units. And so between 0 and 2 seconds, we have that power is 300 over 2t, and our y-intercept is clearly at 0 here. So we'll just, so now we have 150t for when time is between 2 seconds. And so we'll plug that into here. And then when power is between 2 and 4 seconds, we're going to find the equation for our line here. We see that we have a rise again of 300 and again a run of 2 units from 2 to 4. And so we have 300 over 2t plus, let's find our y-intercept here by first using a placeholder, c sub 1. For when time is 4 seconds, we have a value of 0 milliwatts for power. And so that gives us 0. So here we'll just write 150, and for time, we have 4 seconds plus c sub 1. Therefore, c sub 1 is equivalent to negative 600. That's our y-intercept there. And so all in all, we have 150t minus 600 for when time is between 2 and 4. And so we'll plug that into here. Here we have from 0 to 2 seconds, we integrate 150t dt plus, I'm actually going to erase this. From 2 to 4 seconds, we integrate 150t minus 600 dt. And so we have, after we integrate these values, we have 150 over 2 times t squared integrated from 0 to 2. And we have 150 over 2 t squared minus 600 t integrated from 2 to 4. I'm just going to go over this whole thing step by step. You guys can fast forward if it's too easy for you. But basically we have 75 times 2 squared minus 0 for this first part, plus for the second part we have 75 times 4 squared minus 600 times 4 minus 75 times 2 squared minus 600 times 2. We close out these brackets. And then we have 300 plus, let's see, we have 1200 minus 2400 minus 300 minus 1200. Which is 300 minus 300. And in the end, which gives us our final answer of 0 joules or millijoules. It's 0, so it doesn't matter. For when time is between 0 and 4 seconds. And that makes sense, since here we see equal parts of positive power value here. So we get some positive value for energy and an equal parts of that as a negative value here. Therefore, all in all, it comes out to 0. So for this example, the circuit contains 5 elements with their corresponding values of power. Question is, how much power does element 3, this guy, supply or absorb? So we have these 1, 2, 3, 4 elements that each have their values of power that they absorb or supply, but we don't have that value for this element 3. So that's what we're going to find. And for this, we're going to use the law of conservation of energy. Which states that the sum of power in any given circuit at any given time is 0. So this means that the sum of the power of all the elements in this circuit must be 0. And so let's replace P sub 1, P sub 2, P sub 4, and P sub 5 with their corresponding values. We have negative 205 watts for P sub 1, 60 for P sub 2. We'll keep P sub 3 here. We're going to find that value in just a second. P sub 4 has 45 watts of power, and P sub 5 has 30 watts of power. And so this gives us a value of 70 watts for P sub 3. Now let's think about this. Is this element, P sub 3, that has a positive 70 watt value for power, is that supplying or absorbing power? Well, we know that if the value is positive, it absorbs or consumes power. And if it's negative, it supplies or releases. So since it's positive, we know that it absorbs power. And that's our final answer. For this example, we are asked to find the power absorbed or supplied by each element. We also want to find the value for V sub naught. So we have 1, 2, 3, 4, 5, 6 elements in this circuit, and we have V sub naught right here, which we're going to find the value for as well. We need to find P sub 1 through P sub 6. And we also need to find V sub naught. For power, we have the formula V times I. We know that P P is equal to positive V times I if the current enters the positive terminal. We know that power is equal to negative V times I if the current enters the negative terminal of the element. And so here, for P sub 1, we have a current of 6 amps right here going up into the negative terminal of that source. Therefore, we're going to place a negative sign right in front. And then for voltage, we have a value of 30 volts across that. We have a value of 30 volts across that element. And then for current, like I said, we have 6 amps going through that element. So it's 30 times 6, negative 30 times 6. Therefore, P sub 1 has a value of negative 180 watts of power that it supplies. Okay, and that makes sense. It's supplying, it's generating energy to the circuit because it's an independent voltage source, and it is therefore an active element. For P sub 2, we have a voltage of 12 volts, and we have 6 amps also going through it. But the current of 6 amps is going into the positive terminal, so we'll have a positive value for that. And so we have positive 12 volts times 6 amps, which gives us a value of 72 watts. Since it's positive, we can tell that it absorbs power. And that it makes that some sort of a passive element. A passive element cannot generate or supply energy to a circuit. It often absorbs power. We'll find P sub 5, which has a current of 2 amps going through it and a voltage of 28 volts across it. And so, since it's entering the positive terminal, we have a positive 28 volts times 2 amps, which gives us a value of 56 watts for P sub 5. Again, this is a positive value, so that absorbs power. For P sub 4, we have, again, it is also entering, the current of 1 amp is entering the positive terminal with 28 volts across that element. And so for P sub 4, we have a value of positive 28 volts times 1 amp, which gives us 28 watts of power being absorbed. And lastly, almost lastly here, we have P sub 6, which gives us 3 amps entering the negative terminal of that dependent voltage source. And we have a voltage of 5 times I sub naught. So let's just look at this real quick. We know that it is controlled by some current source because it uses current as a variable here. And so this would be a current controlled voltage source. So back to P sub 6. We have, it's going into the negative terminal here, the current of 3 amps going through the negative terminal. And so we have a negative value here. For voltage, we have 5 I naught and the current is 3 amps. Negative 15 I sub naught. And we know that I sub naught is actually given here as 2 amps. And so we'll just plug that in, and we have a value of negative 30 watts for P sub 6. So we found every value of power except for P sub 3. But now we can use the law of conservation of energy to find that. So the sum of power must equal 0. Therefore, P sub 1 plus P sub 2 plus P sub 3 plus P sub 4 plus P sub 5 plus P sub 6 is equal to 0. Let's plug in their values. We'll get negative 180 plus 72 plus 3 V sub naught. Okay, so this is the value that we're going to determine in just a few moments. P sub 4 is 28 watts, P sub 5 is 56 watts, and then minus 30 watts for P sub 6. We have 3 V sub naught is equal to 54, which gives us a value of 18 volts for V sub naught. And that's our final answer. So for this example, an electric heater is rated at 1.8 kilowatts. It is used for 30 days for 15 minutes each day. If power costs 10 cents per kilowatt hour, how much does it cost to use the heater for 30 days? So let's grab our given values here. For power, we have 1.8 kilowatts. And for time, it's used for 15 minutes each day. We can say that that's 0.25 hours. And it costs 10 cents per kilowatt hour. So essentially, the question is this: how many kilowatt hours are used? Now let's think about this. Kilowatt hours. That's a unit for what? Well, we know that 1 watt second is equal to 1 joule. Therefore, 1 watt hour is equal to 3,600 joules. And these are units for energy. And so what it's asking here, how many kilowatts are used, it's asking how much energy is used. Let's break this down per day at first. We know that our formula for energy is power times time. We have a value for power and a value for time. So let's plug those in. The power rating is 1.8 kilowatts. And then time, we're going to use hour. So 0.25 hours. And this equals 0.45 kilowatt hours per day. That's how much energy is used per day, 0.45 kilowatt hours. Now, for 30 days, so here we can multiply our daily energy usage by the number of days. So it would be 0.45 kilowatt hours times 30 days, which gives us 13.5 kilowatt hours total. This is how much energy it uses in 30 days total. So now we're going to find the cost. We know that the cost is 10 cents per kilowatt hour. So since we have 13.5 kilowatt hours, we'll just multiply that to 10 cents. Pretty easy. 13.5 times 10 cents, which gives us 135 cents, which equals $1.35. And that's going to be our total cost right there for 30 days. For this example, we have a boat motor that is rated at 10 horsepower. And assuming that 1 horsepower is equal to 746 watts, how much energy does the motor deliver in 30 minutes? We have 1 horsepower equivalent to 746 watts of power. Therefore, 10 horsepower would be equivalent to 7,460 watts of power. And so it's asking for how much energy does the motor deliver in 30 minutes. We know that our formula for energy is power times time. We have our value for power, which is 7,460 watts, and we have our value for time, which is 30 minutes. And we're just going to convert that into seconds because we want to get it into its standard SI unit form. And so this gives us 13,428,000 watt seconds. We know that watt seconds are equivalent to joules. So this gives us 13,428,000 joules of energy. We can also rewrite this as 13,428 kilojoules of energy. And that's how much energy the motor delivers in 30 minutes. This lecture is included in Unit 1 of our electric circuit analysis series, where we cover basic concepts including charge and current, voltage, and power and energy. The formula sheet for this entire unit is available for purchase at payhip.com/EngineerPeer. Right now, all our formula sheets are on sale for 50% off.